In this video, we'll continue to look at how we can compute the output of a linear and time invariant system from the input x of n using the fast Fourier transform as a computational tool. So we'll continue to assume that x of n has length L, that h of n has length m, but we'll assume throughout that L is much larger than m. So for instance, if we look at the example where we want to, say, bandpass filter a piece of music sampled at CD quality, which will be at 44.1 kilohertz per second, and if we assume that the input has length of 4 to 5 minutes, then L would be equal to roughly about 10 million, while an appropriate filter, so say a bandpass filter, could have, for instance, length m equal to 100 or so. And we've already seen that if you compute the convolution or the output of a linear and time invariant system using the direct evaluation of the convolution sum, which for a finite impulse response filter or for a finite length impulse response would be a sum over the m terms, which would be the length of the filter. So we would have m multiplications per sample in the output signal y of n. So if you look at the total number of multiplications overall, since we have to do this for each of the input samples of x of n, we would have approximately L times m multiplications in total. And the reason for the approximation and this not being an exact value is, of course, that x of n will have some zero values where we don't necessarily need to perform the multiplications. But those cases will be quite small if we assume that L is much larger than m. We've also seen that you could do this in the frequency domain. So what you would do then is you would take the endpoint Fourier transform of the impulse response. You would take the endpoint Fourier transform or the time discrete Fourier transform of x of n, and you would multiply these together to get the output transform y of k, and take the inverse transform to recover y of n. And as long as the length n is selected sufficiently large, which would in this case be L plus m minus 1, then this inverse transform, even though we performed a circular convolution, would correspond to the output of the linear convolution for all non-zero values of the output y of n. So the big question now is, how many multiplications would this require? If we were to use the direct implementation of the discrete Fourier transform, we know that we would require n squared multiplications in order to move from the time domain to the frequency domain. But since n for the circular convolution to be equal to the linear convolution have to be greater than L plus m minus 1, we also know that n squared will be greater than L times m, which is the complexity of doing the direct evaluation of the convolution sum. So by this we see that if you were only able to use the direct implementation of the discrete Fourier transform, then simply moving between the time domain and the frequency domain would be more costly than doing the complete filtering in the time domain. So there will never be any gain in terms of complexity of doing the multiplication in the frequency domain if all that you had was the direct implementation of the discrete Fourier transform. But luckily we have a more efficient option given by the fast Fourier transform. So let's do a cost analysis for the fast Fourier transform in terms of the number of complex valued multiplications. So what you would have to do in order to apply the filtering in the frequency domain would be to compute the endpoint discrete Fourier transform or the endpoint FFT of the impulse response h of n and also the input signal x of n. You will have to multiply these together to get y of k and take the inverse transform to get back into the time domain. So doing the fast Fourier transform, we saw that this costed n over 2 times log 2 of n multiplications. So we have 2 times this for computing the Fourier transforms to get into the frequency domain. Then you would spend n multiplications in order to multiply together these transforms for every value of k, since we have n points in the transform, and there would be another n over 2 log 2 n multiplications to get back into the time domain from the frequency domain. So the total number of multiplications that it would cost to do the filtering in the frequency domain using the FFT algorithm would be 3 times m log 2 of n over 2 plus n. So the question now, is this larger or smaller than L times m? So let's answer the question by considering a simple example. So let's assume that we have an input signal of length 800, we have a filter of length 5, and we need to choose a length for the DFT and the FFT. And we know that this should be an even power of 2 in order to be able to apply the FFT algorithm. And it also has to be greater than L plus M minus 1. And it turns out that the smallest integer power of 2, which is greater than L plus M minus 1 in this case, is 2 to the power of 10, or 1024. So for these numbers we can just compute the complexity. So L times M, the cost of doing the filtering in the time domain using direct implementation, would be 400 in this case, so 800 times 5. If you evaluate the cost for doing the FFT-based filtering, you would end up with a number which would be 16,384. So for this particular case, we see that even though we use the efficient FFT algorithm to move between the time and the frequency domain, the number of samples required to do the multiplication or the filtering in the frequency domain is larger than the number of multiplications to do the filtering in the time domain, so it's roughly 4 times larger. So in this case there would be nothing to gain by doing the filtering in the frequency domain. But if we change the parameters of the examples, we consider, for instance, a much longer filter that we wish to apply, so say a filter of length 200, then we still see that we could choose n equal to 2 to the power of 10, since 800 plus 200 is just 1000, so this would still be larger. So we could still use a 1024 point DFT or FFT in our computations. However, if we look at the cost of doing the filtering in the time domain, it would now be 800 times 200, which would be 160,000, while the cost of filtering in the time domain would remain the same, so at 16,000 multiplications overall. So in this case, doing the filtering in the frequency domain would be 10 times as more efficient as doing filtering in the frequency domain. So what we've seen so far is that when the length of the input signal L is much larger than the length of the filter M, it's typically better to do the filtering in the time domain than use the FFT approach as we have described it so far at least. However, when the length of the input signal and the length of the filter is roughly on equal size, or when the length of the filter M here is quite large, then we saw that the FFT approach was better in terms of the number of complex valued multiplications. So what we will look at next is how we can still use the FFT algorithm for the case when the input signal is much larger than the length of the filter, which is the main interest of this video, by being a little bit more clever in how we apply the FFT algorithm in the filtering operation. So if we consider the filtering problem that we are facing, so we have an input signal x of n which has length L. We wish to compute the output of the filtering operation, or the output of the linear and time invariant system, y of n, and we know that this will have length L plus m minus 1 since the filter has length m, so we get a memory effect of length m minus 1 from the filtering operation, which remains in y here at the end. Now suppose that instead of applying the FFT to the whole sequence as we've been doing before, we just pick out a block of n samples, let's call that x of b of n, from this signal x of n. So here we have the block of length n. Now we can of course compute the circular convolution of this block with the impulse response of the system, to get the block called yb of n. Right? And the reason for the circular convolution here is that we can implement this using the n-point fast Fourier transform in a computationally efficient way. Now if we look at this block yb of n, some of the samples of this block will correspond to the output of the linear convolution between this input blocks xb and the filter, and some of them will correspond only to the circular convolution, or the circular convolution will be different from the linear convolution. So if we do the analysis, we will find that a set of m-1 samples at the beginning of the block yb will be particular to the circular convolution and not equal to the linear convolution, while the remaining n-m plus 1 samples of y of b will be identical to what we would have obtained if we had computed the linear convolution instead of this n-point circular convolution. And the reason that we lose m-1 samples is that, as I said, the filter has a memory length of m-1, so the number of taps minus 1. And in the linear convolution, these would spread out in time, but in the circular convolution, they sort of wrap around and affect the beginning of the sequence. However, what we have here is n-m plus 1 samples that do correspond to the linear convolution. So these are correctly computed samples of the output sequence y of n. So once we know that, we could write these to the output sequence y of n and store them in memory when computing the output from the linear and time invariant system. So now is the question, how do we get the remaining samples of y of n? Well, here we just picked out a block of samples somewhat arbitrarily from the input sequence x of n. So what we could do is we could just repeat this whole process by shifting the block. However, we see that we couldn't shift the block n samples, because if we shifted the block n samples, then we would still have a number of incorrectly computed samples, or samples that would correspond to the circular convolution only, that would end up here, and we would get gaps in the number of values we compute for y of n. But this is easily fixed by not shifting the block n samples, but just shifting it n minus m plus 1 samples, like this. So we pick out a new block which partially overlaps with the previous block, still has n samples, we compute the circular convolution, and by shifting the block only partially, we make sure that these incorrectly computed values arrive at the same position where we've already computed the values of y of n in the previous operation. So what we can do now is just take these values that we compute that correspond to the linear convolution, and we could write them to y of n like this, and we would obtain more values. And we would just continue doing so by shifting the block partially time and time again until we have as many values of y of n as we wish to have. So this is the basis of a method called overlap and save. So overlap because the blocks that we pick out from the original sequence overlap in time. Save because you take the values that you compute by the circular convolution and you simply write them to y of n. And with some bookkeeping, so for instance picking out the first block before x of n even starts and just adding zeros, you can make sure that you get all the values that y of n contain. Right? So these values would correspond to times before we started the filtering operation, and they would not be needed in the output, given that we consider causal filters in these examples. So if we look at overlap save in words, what we have to do is we have to choose a block length n, which has to be greater than the length of the filter in order to compute any valid samples per block. Then we compute the n-point discrete Fourier transform using the FFT algorithm of the impulse response, and we call that h of k. And the thing to note here is that this needs to be done only once, and it doesn't have to be done per block. So if we have a large number of blocks, the complexity of this computation can, in the overall scheme of things, be neglected, and this can be done ahead of time. And then for every block, we pick out an n-point sequence xb of n from the original sequence x of n. We compute the Fourier transform, the discrete Fourier transform using the FFT algorithm of xb. We multiply this with a pre-computed h of k in order to get yb, which is the block y of n's discrete Fourier transform. And then we compute the inverse Fourier transform, or the n-point inverse discrete Fourier transform, to get back the block yb of n. And then we take all the valid values, also all the values in yb of n that corresponds to the linear convolution, and store those to the output sequence y of n. So question now, what is the complexity of this approach? So if we'll assume now that the length of the input sequence is much larger than the length of the blocks, so we can neglect any pre-computation complexity, and we assume that the block length is greater than the length of the filter. Then the number of samples or multiplications per sample of the signal for computing the output y of n using direct convolution is, as we saw, equal to m. So you have to do m multiplications per sample of y of n in order to get the output using the direct convolution. The question is, how many multiplications per sample are required when using the overlap and save method that we just saw? Will it be L over m times log 2 of n? Will it be L divided by n minus m plus 1? Will it be n plus n times log 2 of n? Or will it be n plus n times log 2 of n divided by n minus m plus 1? The correct answer is option number 4. So a way to see that is just to go through the per block computations and do counting of the number of complex valued multiplications. So we get the block xb of n from x of n, so just collecting the values don't require any multiplications. But then we need to compute the discrete Fourier transform of the n-point discrete Fourier transform of this block. And using the FFT algorithm, that will cost n over 2 times log 2 of n multiplications. We have to do the multiplication between x of n and the frequency taps h of k in order to get y b of k. That would require n multiplications, since there are n values in the n-point discrete Fourier transform. Then in order to get back into the time domain, we will have to compute the inverse discrete Fourier transform yb of k in order to get yb of n. And this would require another n over 2 times log 2 of n multiplications, which is the complexity of the FFT algorithm. And then we'll look at the number of valid values of yb that we can store to y of n, so the number of values that correspond to the linear convolution. And we saw previously that each time for each block we compute exactly n minus m plus m such valid values, which are then stored to the output. So if we look at the overall complexity of the method, it would be n plus 2 times this, which would be n times log 2 of n multiplications. And since we look at the number of complex valued multiplications, or the complexity per sample, we divide by the number of valid samples that we compute for each block, which would be n minus m plus 1. And you can write this somewhat more compactly as n times log 2 of n, log 2 of 2n divided by n minus m plus 1. So the question now, is this greater or equal to m, which is the complexity per sample of doing the direct computation? And the answer to this question is, again, it depends on the values of n and m. So in order to finalize the complexity analysis of the overlap and save method, let's consider this coefficient c of n as a function of n for a particular value of the filter length m. So in this case, m equal to 10. So if you plot this expression n times log 2 of 2n over n minus m plus 1 as a function of n, the curve that you would get would look as follows. So we can see that this curve has a unique minima obtained when n is equal to 51, in which case the value of c of n would be 8.1. Now, since we're dealing with the FFT algorithm, we ideally wish to choose n as an even power of 2. So we may not be able to implement the method for n equal to 51, but we could implement it for the next highest power of 2, for instance, which would be 64 in this case, and get the value of c of n, which would be very close to this. So what we see is that if your filter length has length 10, you can do the overlap save method and get only roughly 8.1 multiplications per sample, as opposed to the number of multiplications 10 that would be required in order to do the direct computation in time. So for this particular case, there is not too much to gain, so you would reduce the complexity from 10 multiplications per sample down to just above 8. But if you increase the length of the filter m from 10 to 100, for instance, you would get a new curve which again would have a unique minima. In this case, the minima would be reached for a value of n equal to 833, but the value of this coefficient c of n would only be 12.15 in this case, which means that instead of doing multiplication in time, which would be, or convolution in time, which would be requiring roughly 100 multiplications per sample, or 100 multiplications per sample, you could do it using the overlap save method and only spend above 12.15 samples per multiplication. And also in this case, of course, you couldn't choose the value of 833 for n, since it should be an even number of 2, but choosing, for instance, a value of 1024 would give you a very similar figure. So what we can see generally is that for every value of the filter length m here, there will be an optimal value of n. So we only consider n that are even integers of 2, or even powers of 2. Then you can tabulate what the optimal filter length is for each value, or optimal DFT length or FFT length is for the various filter lengths. So if we have a very short filter, say a 5-tap filter, then doing the overlap save method would still be more complex. But even for quite moderate filters, so filters of length 10 and above, the number of multiplications per sample using the overlap save method is much lower than the number of multiplications per sample that you would need in order to do the direct computation. And the gain is very much increasing as you increase the filter length. So you could, for instance, apply a filter of length 1000 only spending below 16 multiplications per sample, and that's a huge gain. We could also change the procedure in the overlap save method. So if we turn back to the original problem of having a signal x of n, wishing to compute y of n of length l plus m minus 1. When we pick out a block from x of n, so instead of picking out the block of all samples, what we could do is to from the beginning only pick out n minus m plus 1 samples from x of n and making a block of length n by just padding it with zeros or filling the block up with zeros. The key benefit this would have would be that when we apply the circular convolution to go from xb to yb of n, all of the values in yb of n would correspond to the linear convolution of xb of n with the impulse response h of n. However, while the values of yb of n correspond to the linear convolution of xb of n with h of n, they don't necessarily correspond to the linear convolution of the values of x of n with h of n. And the reason is that the filter has a certain memory. So for the first n minus 1 samples of yb of n, you would obtain the convolution from xb of n, but you would miss the memory that would be remaining from the samples before this block in x of n. So you only compute part of the values in y of b. Similarly, if you look at the last m minus 1 values of y of b, they would correspond to the linear convolution of x of b with h of n, right? So they would contain the memory from these samples, but then they wouldn't contain the new information contained in these values in x of n, since these were not copied to the block xb of n. So what we will compute here is only part of the convolution sum. But the nice thing to note now is that the convolution is a linear operation. So even though we haven't completely computed these values, we computed part of them, and by adding values up, we could add the rest of the convolution. So the idea here now, if you do it in this way, would be not to just save the values from yb of n to y of n as before, but you would start with a y of n which is identically equal to 0, and you would add these values. So for the first block, that doesn't really accomplish much other than saving the values. So we would have a set of values which are final computed. We would have a set of values which are only partial here and here. But similar to the overlap and save method, we could now take this block and we could shift it. And we would have the same argument here that yb of n would be the linear convolution of xb of n with the impulse response, but it would be missing certain values from the original signal x of n, or certain contributions, if you will. But the thing to note is that the values that we would compute here, or the partial values, are exactly the values that are needed to be added to these values in order to again make up the final convolution that we have in y of n. So if we now take this block and add it, these values would complete these values, and we would have obtained a larger block of values in y of n. And we could continue this on by shifting the block partially, adding the zero padding, computing the circular convolution using the FFT algorithm, and for each block, instead of saving the values to y of n, we would add them so that these overlapping blocks of partial values would add up to build the entire y of n. And this is the basis of a method called overlap add. So overlap again because we overlap the blocks, but add since we add the blocks together instead of saving them. So also here, if you take care in how you position the blocks corresponding to the original sequence, you can use this procedure in order to compute all of the values in y of n, so the convolution between x of n and the impulse response on the filter. Looking at overlap add in words, it would look very similar to overlap save. So before doing any filtering, we choose a block length n and we compute the n-point discrete Fourier transform of the impulse response, or using the FFT algorithm again. And then for every block, we get n minus m plus 1 values from x of n, and we zero pad them to get the n-point sequence xb, which is the block, which contains values of mx of n plus the zeros that we added. We compute the discrete Fourier transform using the FFT algorithm. We multiply in the frequency domain. We compute the inverse transform to get back into the time domain. But unlike the overlap save, instead of saving the values in YB, we take all of the values in YB and we add them to Y of n. Question is, what's the complexity of this approach and how does it compare to the overlap save method? So if we again assume that L is much greater than the block length, which is greater than or equal to the filter length, and we consider the number of complex valued multiplications per sample for computing the signal Y of n, where the number of complex multiplications for doing the direct convolution would be equal to m. So would the number of complex multiplications per sample for overlap save or overlap add be n plus n times log 2 of n divided by n minus m plus 1? Would it be n plus n times log 2 of n divided by n minus 2m plus 1? Or would it be n plus n times log 2 of n divided by n minus 2 times m plus 1? And the correct answer is option number 1, which is the same answer as for overlap and save. And we can get to this answer by again following the steps of the overlap save or the overlap add algorithm. So we will get n minus m plus 1 values from x of n and zero pad this to the sequence. We would compute the FFT, which would require n over 2 times log 2 of n multiplications. We would do the multiplication in the frequency domain, which would require n multiplications since we're working with n-point DFTs or block lengths n. We would compute the inverse transform, which would cost n over 2 times log 2 of n multiplications, and then we would add the values in YB to Y. And in order to get the number of multiplications per sample, what we need to figure out is how many values of Y of n do we in general complete by adding YB of n to Y of n. And that's equal to the shift in terms of the blocks, which is the same for the overlap save and the overlap add algorithms. So we would complete n minus m plus 1 values in each step. So the number of multiplications would be the sum of the multiplications we do to the filtering per block divided by n minus m plus 1, which is the number of values that we complete per block or per shift. So the overall complexity in terms of complex valued multiplications for the overlap add would be the same as the overlap save and would be given by this formula that we've seen before. So the optimization of the block length for overlap add would be the same as for overlap save. To summarize, what we've seen in this video is that even for very long input sequences, we can use the fast Fourier transform to efficiently compute the filtering operation in the frequency domain, or to filter in the frequency domain. And the way to do this is to take the input signal and divide it into overlapping blocks. And there are two very similar ways that we can do this. One is overlap save and one is overlap add, and we saw how these two methods worked. Both have the same complexity in terms of the number of complex valued multiplications per sample, and it's given by this formula that C of n is equal to n times log 2 of 2n divided by n minus m plus 1, where m is the filter length and n is the length of the block that we use in the fast Fourier transform. And we also saw that there is an optimal value of the length n for each value of the filter length m. So n will generally be quite a lot larger than m, but much shorter than the total length of the signal that we wish to filter.